first one is that sunlight is by far the most abundant source of energy that we have. We have about 120,000 terawatts of energy incident on Earth, and about 36,000 of it is on land. And to show you the comparison between sunlight and other types of renewable energy, sunlight is actually the only source of energy that can actually meet the 30 terawatts of the world's demand by 2050. And to put that into perspective, and with sunlight, we only need to cover 0.8% of the surface of the land with 10% of a solar device. And to make that into perspective, if we consider this the map of the world, we need to cover all the equivalent area of South Africa only in order to actually power the entire world. We can actually spread it around a little bit. The choice of South Africa is really not really taken into account. The second fact is that the chemical fuels, if you compare different energy storage technology, chemical fuels has the highest energy density and power density, even if you compare it with the most advanced battery and supercapacitor. So chemical fuels means that you store it in a chemical bond. And the third fact is that, unfortunately, electricity is still inaccessible in many locations. In fact, if you take a look at the energy use, we actually use 83% in fuel and only 17% in electricity. So that means we have large infrastructure for fuels, but not so much for electricity. Now, if you put these three facts together, I think it's pretty logical, and it's really not that hard to actually go into the conclusion that probably the best way to go is making fuels from sunlight. Now, can we actually do that? It turns out that the very nature, has been doing that all along through the system that you all know very well called photosynthesis. Basically, plants took sunlight in order to drive this chemical reaction. It takes carbon dioxide and water and use sunlight to transform it to some kind of sugar, this is glucose, and release oxygen. So now can we actually make similar things? If we take a look at the different chemical reactions, water splitting is actually the chemical reactions that's the easiest, relatively the easiest to do with the amount of energy that we can get from sunlight. In this reaction, which is an uphill reaction, which means you need energy, you take two different molecules of hydrogen, and if you give energy, in this case through illumination, you can rearrange the bonds. There goes the animation. You form two molecules of hydrogen and one molecule of oxygen. And you can then use this hydrogen as a storage itself, so this is a fuel itself. You can burn it with oxygen later and get energy and water back. Or if you don't like working with hydrogen, we can actually combine it with carbon dioxide in a reverse water gas shift reaction, which we already know, forming syngas, feed it into Fischer-Tropsch reactor, which we already know and doing at a large scale right now, and make any hydrocarbons that you want. So the key process is over here. Now, in order to do this water splitting reaction, we need to use a material to actually capture the sunlight and perform the chemical reaction. And the class of material that we use is the inorganic materials called semiconductor. Inorganic semiconductors. And I'll explain a little bit of a semiconductor in this diagram over here. So in semiconductor, or in any materials for that matters, there are two different energy bands in terms of energy levels that are relevant to us. And it's stated over here. One is the VB, or the valence band, and the other one is the CB, or the conduction band. And the characteristic in a semiconductor is that the conduction band and the valence band is separated by an area called band gap. And in this band gap, there are no energy levels, which means there are no electrons that can occupy this level. The electrons can either be here or here. Now, in a valence band, the characteristic is that it's full of electrons. So you can imagine if there are like three spots or three places in the valence band, all of them are filled with electrons. And as such, because it's all filled, you can imagine being in a cramped room such as today, that is pretty hard actually to move around. Therefore, the electrons in the valence band are in a lazy state or immobile state, so they cannot really move around a bit. So they really just stay at their place. Now, what happens if you give energy to them? For example, with light, this electron can actually overcome the band gap and go to the conduction band. And now, in the conduction band, the characteristic is that it's empty of electrons. Because it's empty, the electron can actually move around in the conduction band. In the contrast, in a valence band, we have now, as a result of the excitation, an empty spot. Now, if you have the empty spot here, electrons seeing this are now able to move around a little bit. Or if you actually want to see it the other way around, it's actually the empty spot that is actually moving around. And we like to see it that way, and the empty spot is called hole, the electron hole. So as a result of excitation with light, we got an electron in the conduction band and an electron hole in the valence band, both of which are mobile now. So now that you understand a little bit about the semiconductor, we put it in the photoelectrochemical cell and perform the whole reaction now. So this is the semiconductor. We combine it with a metal counter electrode connected with wires and immerse them in the electrolyte, which is basically water. This is the picture that I've shown before. The valence band, conduction band, we illuminate and create an electron in the conduction band and hole in the valence band. Now I think you're comfortable with the concept. We don't need to use the figure, and I just change it with the symbol over here. The electrons then, since the semiconductor that I chose here is an anode, which means oxidation happens on the surface, hole will actually go to the surface and perform oxidation reaction, and oxygen will bubble from there. Electrons on the other side goes to the metal counter electrode and reduce water to form hydrogen at the other side. So the oxygen and hydrogen that we produce are formed in a separate location, and then we can collect this hydrogen as an energy storage. Now, the semiconductor is the most important thing in this configuration, or one of the most important things. And as such, my PhD thesis was focused on finding one of this ideal semiconductor. And the semiconductor that I focused a lot is bismuth vanadate, or BiFeO4 over here. This is a class of metal oxide semiconductor. You may not realize that bismuth vanadate is actually present in your daily life more than you think. It's present as a yellow pigment in paint, in printing ink, the covers of magazines and such. And the presence of bismuth vanadate in the current World Cup is actually more than what you think. On the other hand, bismuth vanadate is also photocatalytically active. Which means that using light, we can use this photon energy to actually perform a chemical reaction. But when we started to look at this material about 4 or 5 years ago, there were still a few open questions remaining. First, the performance that's reported were modest and they are not really uniform. That's mainly caused by the unknown performance limiting factors. So what we have done is that we tried to actually focus in answering this and tackling them systematically. As mentioned, we made our bismuth vanadate with a very simple technique called spray pyrolysis, depicted over here on the right. Basically, you just take a liquid solution over here containing bismuth and vanadium, take a bismuth salt, vanadium salt, put it in a liquid, dissolve it in a liquid, and then you fill it into a nozzle and then you spray it onto a substrate, glass substrate, which is located on a heating plate. So it's pretty much like airbrushing on a heated substrate. And as a result, you get this yellow color film. It's pretty thin, about 100 to 200 nanometers, on top of the glass substrate that we have over here. To make a long story short, I'm just going to show the performance that we have with our bismuth vanadate. So this plot, the y-axis is the photocurrent, or the performance of our device, and the progression at the beginning. The slope is pretty gentle because we tried a lot to optimize the deposition parameters. But as soon as we do that, we started actually trying to identify this different performance limiting factor, be it catalysis, conductivity issues, absorption issues, and started tackling them systematically. And as you can see, the progression, the rate of progress is becoming more steep. And as a result, we get about 4 milliamps per square centimeter with our bismuth vanadate. And if you compare that with the other reports in the literature, it's clear that we have one of the highest performing bismuth vanadate until very recently, about 4 or 5 months ago, that another group in Madison, Wisconsin came up with a better bismuth vanadate. It's okay. In the future, everyone's famous for about half an hour. We got 6 months. So it's all good, but the problem with this is that all these photocurrents that I mentioned are actually at a bias potential of 1.23 volts. What it means is that we still need to provide additional energy, additional bias potential in order to actually claim this photocurrent. And if we take a look at the formula here, the solar to hydrogen efficiency, which is the metric that we all interested in at the end, the applied voltage here has a negative term in front of it. And that means that if we apply any bias potential, it is actually hurting the efficiency, decreasing the efficiency. So what we wanted to do next is just to get rid of this bias potential and claim the full efficiency. And we did that in collaboration with the solar cell group at Delft, Professor Miro Zeman and Arno Smets, in this hybrid photoelectric configuration, where we took bismuth vanadate and combined it with this amorphous silicon solar cell. In such a way that when you illuminate with sunlight, bismuth vanadate actually only absorbs part of the sunlight, which is the blue part of the sunlight. And the red part of the sunlight is usually transmitted, and this is usually just lost. You just lose this part of the sunlight. But now if we have this thin film silicon solar cells at the back, the solar cell can actually take this transmitted light, which is usually lost, to provide the bias potential that the bismuth vanadate needed. So in a way, we are providing the bias potential using the transmitted light, using the light that we initially lost. So this is the device in action, or in photograph. It's not really fancy at all. And as a result, this is the photocurrent that we see when we just took that sample and put it in water without any additional bias potential, and then we measure the solar to hydrogen efficiency, and we get about 5% solar to hydrogen efficiency, which is one of the highest performing efficiency as mentioned. Finally, seeing is believing. So I'm going to show a short video. Before that, I'll explain a little bit what you will see. So at the bottom over here is the device. So this is where the bismuth vanadate is located with the tandem device. And this is the metal counter electrode, and light's going to come from the top at the moment, or in the video. And oxygen is going to bubble from here, and hydrogen is going to bubble from the other side. Finally, before I end, I would like to acknowledge this respective people that I have listed over there. But now it's gone. It's fine. All the people, the promoters again, my colleagues, my collaborators, my research partners, without whom I wouldn't be able to finish the thesis, let alone be here to receive the award. And the funding agency, and of course, thank you all for your very, very, very kind attention.